Right. This is a supplemental lecture um, to the patterns of growth and decay. I'm recording this video because the original, in the original videos that were made like 5 years ago, uh, I was I was illustrating the patterns of growth and decay, and at the time, that was it was made in such a haste, right? Everything was in a rush, and the videos were accidental products of the pandemic situation. So some content was not really well made. I mean, the explanations were rather sketchy, and sometimes uh, uh, chaotic, even chaotic. So let me clarify, because I I realized that in the is this being recorded? The next question is it being recorded? Um, I hope so. And yeah, I guess it is being recorded. All right. So let me clarify a couple of things. Okay. So when we talk about growth, right, such as revenue, growth in revenue, okay, use. So obviously, growth is something that happens over time. So this horizontal axis would be time, vertical axis would be dollar value because it's revenue, and the growth can take three forms. And this was also discussed in the original time value of money video. Uh, the growth can, most commonly, you might think growth would look rather, it can be erratic or irregular. But if it is growth, overall, you can identify some linear trend line, right? A linear trend line, like this. Yeah, that's growth. And this type of growth is linear, right? Linear, right? However, growth can take different patterns, such as what do I use? Let me let me. What kind of color would I use? Okay, so maybe green would be the best. What's this one? And let me. So yeah, okay. Growth can take this pattern, or it can also take. Uh, it can also take this pattern, right? And this type of pattern is called, uh, this is exponential, right? And it will be defined by exponential function. In other words, y, in this case, y is dollars, right? Revenue, right? Is a raised to x. For example, obviously, if let's say a is 2. If x is 1, right? Uh, y will be 2. If x is 2, y will be 4, and so on, right? That's exponential. And uh, this type of growth, this pattern is called logarithmic. It's logarithmic. Logarith, uh, logarithmic. So in this case, right, uh, y is log of x, right? So these are three ways, right? Three ways we can approximate the growth patterns, right? Of course, in reality, it doesn't really happen this neatly. It doesn't show these neat patterns. I mean, in reality, it would be more like this, and approximation of that uh, irregular pattern, right? Uh, Approximating it as some, regular pattern, right? A pattern that is, easily identifiable. It's, that technique is called, curve fitting, a mathematical technique for, identifying the best, uh, best equation for that irregular line. That's called, curve fitting. But usually, we can use like three approximations. So that's growth, right? But in case of now, let's think about. Oh, I forgot to do this. But in case of decay, so uh, let's see if I can drag it down. Yeah, decay, right? Uh-uh. So let me also suppose something like population. Also, amortization. Amortization was uh, showing you how the principal decays over time. But whether it is principal or population, right? Let's say there's a decay. Decay can also take three possible patterns, right? Like straight line, but linear. But as I said, it's not really, nothing in real life or nature doesn't fall in a straight line like this. This would be just an approximation of something like this, right? And of course, you will see this kind of decay. Also, you may see this kind of decay. Now, this kind of decay is called logarithmic, of course. I spell it uh, logarithmic. Okay, just let's be, phonetically, let's logarithmic. And this decay is then, of course, exponential. Okay. So you can see in general you can identify or you can see a couple of properties in always exponential functions. I'm sorry. This one is it's vice versa. Hmm, Am I? Uh, if it is exponential, the slope will have to be steeper as time goes on, right? So this would be logarithmic. And then where is it? This would be logarithmic because the slope is getting flatter, right, as time goes on. First, early on, it drops drastically, but the rate of decay is getting uh, flatter and flatter, or slower and slower, right, over time. Whereas exponential decay would show uh, the opposite, the mirror image, right? Because the slope is flatter early on, but as time goes on, slope is getting steeper and steeper. You see the uh, same pattern here in exponential growth, right? Slope is flatter early on and getting steeper and steeper as time goes on. Logarithmic, slope is steeper early on and uh, getting flatter and flatter as time goes on over time. So, so this is, how we can define uh, growth and decay. All right. So that's the supplemental lecture to the time value of money. Okay. All right. Let me stop this recording. Stop sharing and meeting.